So next, I'd like to introduce another investigator, part of the Firefighter Cancer Initiative, Dr. Shanta Dhar, to present on electrical vehicle and heavy metal exposures. Dr. Dhar received her PhD from the Indian Institute of Science in Bangalore, India. Her graduate work was in the area of inorganic chemistry, with the overall goal being to develop copper complexes to affect photocleavage and double-stranded DNA at longer wavelengths. Her previous work included developing fluorescent sensors for the detection of various DNA lesions and a focus on nanocarrier-mediated delivery of platinum-based drugs for potential applications in cancer. She joined the Department of Biochemistry and Molecular Biology at University of Miami Miller School of Medicine in June of 2016. Thank you so much, Shanta Dhar.
Thank you. Thank you, both of you, for that introduction. And probably you are all wondering, what is she doing here? You know, all the work she has done in some sort of chemistry, and I still do that. And I'll try to connect the dot and tell you how we can be part of the FCI team and investigate metals in the context of firefighters. Okay. Okay, so this one. Okay, so I'll tell a little bit about electric vehicles, not how they work, how the battery works, but how they are different than conventional batteries, and then try to dig in and see how we can do things with metals. Okay, so probably you have already seen that the use of the electric vehicles are rising, and so the number of fires. We see more and more fires. Actually, the ratio between the number of electric vehicles to number of fires is much higher. So fires are increasing, and that's a good thing, you know, how Elon Musk said that he himself alone is making the environment better than all the people combined in the world. So probably we are in a good place using electric vehicle, but there are also a lot of unknowns. And I think being scientists, that's our responsibility to know what these vehicles can do both in short term and long term, particularly when they burn. And this is a picture which one of our trainees put together, and this is really just a guideline from Tesla for the fire hazard, but it's not a comprehensive list of things. And if we look through that particular picture, there is nothing about metals or any other potential toxic materials mentioned in that particular picture. So there are a lot of unknowns, and that's what I'm trying to say here. And these challenges continue because most of the fire departments are not aware of what is present in this fire, and then not much precautionary steps are taken by the firefighters. And the one thing we do know that these fires from electric vehicle battery, they have a lot of hydrogen fluoride and some other toxic agents. Now, hydrogen fluoride can react with many other things and give unknown toxic components which we still don't know. But there are a lot of metals which can be present in this when this battery is burned, such as cobalt, nickel, manganese, and then aluminum, copper, and then many others. And then so much that we can also have things like rare earth minerals and elements that can be very, very toxic. And you know, for a long time, I have worked with a metal which is platinum, and probably many of you know is one of the most widely used chemotherapeutic. And what we say that, you know, if cancer patients they get cured and then live longer. And if you take the white blood cells from this patient, you can still detect platinum by mass spectrometry. So these heavy metals stay on. Even you think they're getting cleared, they're not completely cleared because they can get incorporated in our DNA and then proteins, etc. And it's difficult to know what they're going to do. And so I'm going to take a pause and a little bit talk about what can we do. So again, there is very little known. There is one report which talks about effect of hydrogen fluoride, and then nothing else. And then this particular study, which was done sort of in a simulated manner, where they took the internal combustion engine vehicles and two types of electric vehicle batteries and looked at the particles in the chute. And if you look at this particular picture, you see the metals are drastically different between these two types of batteries. In the conventional batteries, you see very low level of metals, but in both the kind of electric batteries, these metals are very highly present. On the other hand, you have those PHs, which are not much different. Actually, the conventional batteries, they have more of those polyaromatic hydrocarbons. So metals is really a problem in electric vehicles batteries. And I think I moved. So I wanted to show you why, what we are doing and why we are doing. And I don't know how, I still am going to find out. Alberto was able to track me down that I work on metals. And then, he started talking to us, what can you do in terms of metals in these fire burns? And so I put a lot of picture there, a lot of structure there, but these all molecules were made in my lab over the years. And what we do, on the blue on the screen, you see a molecule which is cisplatin, the chemotherapeutic. And it's a purely inorganic compound. That's why we love it so much. Because any drug you will talk about, there is at least one carbon atom. And that particular molecule in blue has no carbon atom. So it's completely held together by metal. And the way cisplatin works, it interacts with DNA and forms cross-links, and then that is how it then shows chemotherapeutic effect. What my lab pioneered was to make prodrugs of this particular drug, because as I told you, cisplatin has a lot of side effects. So we started working on molecules which can be activated in the cancer cell and then locally produce this drug. So to do that, we of course always have to track down this product, whether they're going to the cancer cell, whether they're going to the nucleus, and so on. And so we developed these methods where we can detect this heavy metal, platinum, in different biological systems, and that is where we come. And not only that, to give more specificity, we often load these drugs in different kind of nanoparticles, which can take them to a particular tumor site, to the brain, or to a particular area of interest. So we also have to track these molecules in different biological compartments. And in that context, we do not only platinum, but we do cadmium, we do zinc, we do selenium, all these different heavy metals. And I think I'm moving backward. And not only that, recently my lab developed a molecule which inhibits fat transport to the mitochondria, and that way it inhibits fat metabolism by cancer cells. So we are also able to detect these metals in different, conjugated to different proteins, different DNA molecule. And then in this particular example, what we have done, we are looking at how metal complexes can distribute in a primary tumor such as breast tumor and the metastatic brain tumor. So we are able to detect these complexes not only in one place but different other places by playing with their structure and how we determine that. And when we can do that, we can simultaneously work at cells which are proliferating. So with this expertise, we wanted to understand how we can detect metals in different biological samples. And in this case, our sample of interest is Firefighter toenails. And because these toenails, they grow slower, we can collect them for a longer time. There are not a lot of non-Firefighter controls you can have. And then we can take these toenails and conduct mass spectrometry and simultaneously detect 29 heavy metals. And I listed them there. And the ones in red are, we already know that they're present in electric batteries, electric vehicle batteries, okay? So the idea was to use this method to quantify the toenail metal. So typically, it's a lot of work. So typically, you take the toenails, you clean them up, and then you do a digestion mechanism. And then once you have the sample, and then we conduct inductively coupled plasma mass spectrometry. It's not a very old method. Actually, this method was invented after I was born. I think 1980 was the first time. It was a theoretical mass spectrometry method, and I think probably late 80s, there was only one instrument which was sold, and then over the years now we see more and more use of this kind of mass spectrometry. You can do this measurement at a very low concentration, parts per billion. You can detect with high accuracy, and you can run this sample really with a broad elemental coverage. So the way it works, you take the metals, you take it its elemental state, you melt it down, and then you look at the metal, and then metal ions. So you can see here, if we take the toenails and then do all these, we always run some standard samples for each metal, each of these metals, and there are some of the standard curve. You can see the resolution is very high, the R² is almost 1. And then just to show you some of our results, these are from 3 different cohorts of Florida firefighters' toenails, and I have only included the metals, heavy metals, which are relevant to, which have potential cancer risk, and we can detect all these metals in these toenails. So the idea would be this very similar, that firefighters who have been on the site for electric vehicles fire, we would take the toenails and analyze all these different metals, follow these over time, and so on. So I think the significance of toenail analysis is high because, again, it is fast, it is non-invasive to collect. You can have a lot of different controls to validate your data, and then if we understand all the metal exposure, then we can provide some guidance or do future work where we can understand how much of metal is okay and how much is not by complementing the findings with lab-based data. And not much is really known looking at the toenails and metal exposure, but there are a few reports where you can see that heavy metals like cadmium, copper, lead, or zinc, and manganese, etc., were usually found in nails of oral cancer patient, or toenail arsenic has been associated with breast cancer or cervical and prostate cancer risk. And then same as higher lead concentration in the toenail also can predict cancer risk. So the idea would be really to dig down at those particular metals, and then if we understand how much is present, then do some of the lab-based studies. We can look at different concentration of these metals and oxidative stress, DNA damage, DNA alkylation, and so on. And so that's all I have here. And so this is, of course, a teamwork. One of our trainee, Kevin, who started the work, along with Dr. Sooner, and then now Shrita and Alex have been continuing with this work. We have already analyzed a lot of toenails, and then we have a lot more sitting there to be analyzed. We not only just analyze the sample, we also do different concentration, going back and running with, again, standard, revalidating the data. And I'm happy to take any questions which you might have.
Hi. Quick question. So metal fires are usually fought with the Class D extinguishers, which some formulations contain copper. Two questions actually. Do you have a correlation with what kind of fire the firefighters responded versus the toenails you analyzed? And do you see specifically higher metal levels in firefighters specifically fighting vehicle fires?
We don't know that.
Okay.
That's a good question. And there are a lot of such things like, all metals, they do not get absorbed on the toenails at the same rate,
Yeah.
right?
Mm-hmm.
Keratin is different. So those are always there, and I think having all these non-firefighter controls will be really helpful, or just following over time, immediately after the fire, and then over time, those will definitely serve as control to get all those parameters down.
Thank you.
Dr. Dhar, you have a question online. How long, if you can just repeat it?
How long will you follow firefighters with electric vehicle exposures? You have to answer that.
Okay, so I'll jump in. But please jump in on the measurement of the tissues. So the question online that we have is, how long will you follow firefighters with electric vehicle exposures? And so we have some active cohorts right now where we follow firefighters year after year. And in some of those cohorts, every quarter, so every 3 months, we ask them to provide a toenail sample to see what metals there are there from time to time. So for example, in the cohort urban search and rescue firefighters, those were samples that were submitted every 3 months there. So I don't know if you want to comment a little bit on sort of like the delay and measurement of metals within the toenails.
Yeah, I mean, I think once the toenails are collected, there is no way you will lose the metals. So I think whatever you follow the collection, that should give the results. That will give the true picture. There is no loss.
And the sample collected from the toenails, from toenail clippings at the front of the nail, is usually a picture of the last, say, like 6 months to 9 months of it, depending on, obviously, the person's toenail sample and their frequency of cut.
Yeah.
Yep.
Yeah. And then, also, I think if we understand this, the metal contaminant, the batteries are always evolving, right? So that like nickel batteries are coming up instead of lithium-ion batteries, for example.
Exactly.
Right? So I think it will be very interesting to compare those metal profiles between different batteries.
Absolutely. Yeah. Any other questions we have for Dr. Dhar? Okay, thank you very much.